Hi all, today we're gonna talk about chirality and the concepts related to it, like enantiomers, diastereomers, and meso compounds. Chiral carbons are having different groups around them. What does it mean? Look at this uh, compound. See, you have a carbon here, one chlorine connected, one iodine connected to it, one bromine, and one hydrogen. This central carbon is called the chiral carbon. So we call it also a stereocenter. Also, we call it chiral center. You can hear about all of these, which means the same, which means that we have chiral carbon. Let's see if we can find chiral carbons in the followings. Is chiral. Let's see. We have one CH3 connected to it, CO2H connected to it, hydrogen connected to it, and OH connected to it. So there are different groups connected with this carbon. This carbon is called the chiral carbon or stereocenter. What about this CH3, guys? Do you think this CH3 is chiral? So you can see that CH3 has three hydrogen and another bonding to another carbon, right? So this carbon is not chiral, right? Because it has the same groups, three hydrogens attached to it, okay? So this carbon is not chiral, this carbon of the CH3. What about the second one, guys? This carbon in the center is also chiral. What about this CH3 here, guys? This CH3 is not, this carbon in the CH3 is not chiral because it has three hydrogens around it, which are the same groups. What about this one, guys? The third one, also this compound is, this carbon is chiral here. In this compound that are line angle, I recommend you to put the hydrogen first because you see that, as you know, in these compounds hydrogens are not shown. So first we're gonna put the hydrogens. So you can also put in the other ones two hydrogen here, two hydrogen here. We're going to talk about them later, but let's look at these three hydrogen that and the carbon that is in the center of them. You can see that in this compound, this in this center, you have one hydrogen, one CH3, another CH3, and another compound attached to it. So basically, in this carbon connected to 1, 2, 3, 4, 5, 6 other carbons. So pay attention, guys, whenever you are examining a carbon center, look at what other connections to it. If it has other connections, it's also important because it makes a difference from other carbons. So here in this carbon, I have one hydrogen, one CH3, another CH3, but another connection, which are 6 carbons. What do you think? Do you think this carbon is chiral or not? This carbon is not chiral center, is not chiral because it has two CH3 around it, okay? What about this one, guys? This one has a one hydrogen, one chlorine connected to another carbon, which also is connected to 2CH3. This from the left side is connected to the another carbon, but this carbon is connected to 4 other carbons and 1 methyl group as a branch. So you can see that this group is different from this group. Okay, although you might say that, okay, this is carbon and this is carbon, but other also carbon that is attached to these also important. So what do you think? So this carbon is chiral. What about the last one here? That is, there is a row to it. So you can see there is a CH3, there is 2 carbon in the left side of it. There are 1, 2, 3, 4, 5 other carbons with other attachment in its right side. So this carbon is also chiral center. What about these carbons? This carbon here, this carbon here, this carbon here. These carbons are not chiral because there are 2 hydrogen attached to each of them. So 2 hydrogens means that there are the same elements attached to it. So it's not gonna be chiral, these 3. What about this CH3 and this CH3 and this CH3? These are also not chiral because there are 3 hydrogens which are the same groups attached to them. After we talked about the chiral carbon, now I want to introduce another important concept when we talk about chirality is R and S configuration. What does it mean? Identical twins have really similar faces, right? But mothers or other people know how to distinguish between them, right? So one of them has for example, different nose, a little bit different nose, or different color in eye. So there is a way to distinguish between them. Also, in chiral centers, there is a way to distinguish one chiral center from another chiral center. And they're gonna name it based on that. So let's talk about it. How to assign R or S configuration to the chiral centers. First, we should assign a priority from 1 to 4. So because as we know, there are 4 groups or 4 different groups around the chiral center, so we should assign priority to them. What are the priorities? Priorities based on atomic number. The higher the atomic number, the higher the priority. If you go from 1 to 2, just count based on their increasing the number. 1, 2, and you can see it's 3 here, right? So if it goes clockwise, see 1, 2, right? It's clockwise. We call it R configuration. Okay, but if the numbering is going counterclockwise, it's gonna be S configuration. We can assign the priority. So do you think if we have these groups around our chiral center, do you think which of these is gonna get the priority? Yes, this one, because after CH2, we have oxygen, which is higher prior when you look at CH2 is after CH2. So you should look at if your first elements after the chiral center are the same, you look at the one after them is higher prior group, oxygen compared to carbon. What about this one, guys? This one, nitrogen or carbon. Nitrogen is prior to carbon. So you can see that because it's higher atomic number, nitrogen compared to carbon, and also here oxygen compared to carbon, they're gonna get the higher priority. Let's do some RNS configuration, guys. What do you think? Let's do that. So which one gets number one here around the carbon? OH, then CH2, CH3, because it's more atomic number. So which one here gets higher number? First OH, then number two is gonna be CH2, CH3, because if we have the same carbon, we look at after that, because it's the more carbon atoms here, this would be number two, CH3 will be number three, and hydrogen is gonna be number four. Look at hydrogen. Hydrogen is in the dashed format. So it means that our configuration, whatever we find, is going to be, we just write it down. We don't need to reverse the configuration. So you can see that 1, 2, 3, and we go based on the increasing numbering. So 1, 2, and 3. So it's going to be clockwise, is going to be our configuration. What about the second one? Second one, for sure, nitrogen first. Then it's going to be the COH. Because is oxygen after that, which is higher atomic number priority. Number two here, number three, and number four. So here we have also our configuration. Because again, hydrogen is in the -4, the R configuration is correct. You can see it's a clockwise format. If the hydrogen is number 4 and it is in front of picture, the configuration is reversed. So if you have hydrogen and you see that is in the wedge format, it means that we should reverse whatever we got until now. We should reverse the configuration. For this molecule, you see that we have fluorine, OH, hydrogen, and CH3 around the carbon. So we start assigning the priority groups. Here, fluorine is higher prior because the atomic number is 19. Then O in the OH. Why? Because oxygen is the second prior. Is the atomic number is 16. Then carbon in CH3 is going to be number 3 because is the atomic number of carbon is 12. And the last one will be hydrogen. So we're gonna find the configuration. What do you think is the configuration in the second compound that I'm arrowing to? Because it's counterclockwise, because see 1, 2, and 3, right? Is counterclockwise, so it's gonna be S configuration, but because hydrogen is in the front of the picture. Why? Because it's in bolded form and you see it's in wedge form. So it says that the hydrogen is in front of picture. Then we should reverse the configuration from S to R configuration. So S becomes R. The final that you should write for sure in your paper, it should be R configuration. You can also, like me, show me the process, like here, S becomes R configuration. Here we have two chiral centers, right? These two red ones. So we need to find for each of them RNS configuration. So it depends how many chiral centers you have. You need to find for all of them RNS configuration. Here, let's do for the first one from the top, this carbon. Which one is going to be number one around it? OH, right? Number one. Now let's see. These groups is going to be number two or this group. This group on top will be number two. Pay attention, guys. When you have a carbon with double bond, it means this one has 2 times more priority compared to the bottom one. So this carbon which has double bond has more priority compared to the single bond carbon to OH. Here, this would be number 2, this would be number 3, and this would be number 4. So we have 1, 2, so that would be S configuration. Did we miss anything, guys, here? Yes, hydrogen here is in front, right? What should I do? I should reverse the configuration. So here you see that here 1, 2, 3, 4, it would be S, but the S becomes R because more hydrogen is in front. When number 4 is hydrogen as in the front, like a wedge, when you see wedge, it means that we should reverse the configuration. Let's do the second one, guys. Here, the bottom carbon, that is red, here is number 1. Now, do you think this carbon, number 2, or this carbon? This carbon, guys, in the top, which is connected to, like you can see, OH is connected to another carbon. So this one is gonna be more prior because there are more carbons inside it. So number 2, number 3, and number 4. So it's gonna be 1, 1, 2, 3, and 4. So it's gonna be R configuration for this carbon, but because the hydrogen is in the front, is going to be S configuration. We have previously talked about isomers. We know that isomers have the same molecular formula. We have also talked about constitutional isomers, which they have different connectivity between isomers. And today we're going to talk about the isomers that have the same connectivity, and these are stereoisomers. If the molecule has a chiral center, as we said, we call it a stereocenter, so it becomes chiral, and we should name it based on its characteristic. We should distinguish it from enantiomer or diastereomer. So whenever you have a chiral carbon, you can realize if you have enantiomer or diastereomer. If you don't have a chiral carbon, you will have a achiral. So just like, do you remember we have a normal and abnormal, right? In the English language, is the same. When A comes in front of it, it becomes achiral, it make it negative. So achiral means not chiral carbon. So the carbon that does not have different groups of around it. So the example would be cis-trans isomers, or the carbons that do not have the different groups around them. Let's talk about enantiomers. Look at the picture in the left side. If you put your hands in front of each other and mirroring your hands, you see that your hands are mirror image of each other, right? But if you put one of your hands on top of your other hands, you see that they are not fitting on each other when you put one of them on the other one, like the right picture. We say that so the hands are mirror image of each other but are not superimposable on each other or superposable. The same happens in enantiomers. In enantiomers, we have two compounds. If the two compounds can be mirror image of each other, like the left picture for hands, but when we put one of the compounds on top of the other compound and they are not fitting on each other, so we call it there are not superposable or there are non-superposable compounds. When the two compounds are mirror image of each other are not superimposable, there are enantiomers. If you try, guys, to remove like a screenshot this left picture and put it on the on top of the right picture, like you do the same for your hands. Put them on top of each other. Are they superimposable or superposable? If we try to uh, take the left one and put it on the top of the right one, you see that they are not the same. You see that OH will be on top of CH3 in the right side and CH3 will be on top of the OH in the left side. I just did a screenshot of the left one. You see it's the same. And I put it on top of the right one. And you see that they are not superimposable here. You can see that, see? So these are enantiomers. These two compounds are enantiomer of each other. Let's find R and S configuration. Let's more practice. So this would be number 1. This would be number 2. This would be number 3. And this would be number 4. So it's going to be counterclockwise is S configuration. Because the hydrogen is in the back or in the dashed form is S configuration still. What about the right one? Is 1, 2, 3, and 4. This one would be R configuration. So pay attention, guys. Enantiomers always have opposite R and S configuration. It means that if one stereocenter is S configuration, the same stereocenter in the other compound would have an opposite configuration, which is R here. So these two are enantiomers of each other, and as you see, they have also opposite configuration. And we call these two compounds stereoisomers. If you remember from the previous slide, when I talked about stereoisomers, enantiomers are the subdivision of stereoisomers. You can see that in these two compounds, which one has S configuration and one has R configuration, they have all the same connection. See, both of them has COH, they have both hydrogen, they both have OH, they both have CH3. Just the location of them around the same carbon is different. So you can see that in here COH is here, the same location, but CH3 and H and OH have flipped. Enantiomers are also optically active. What does it mean? The compound, when we put it in a specific instrument, which we call it polarimeter, they're gonna be able to rotate the plane of a plane polarized light. So it's a specific light and it can be it's able to rotate it. Okay, so enantiomers are all optically active. So this is the same pair of enantiomers that we had in the last page. You see that these are enantiomers. They have S and R configuration and they are also optically active. Enantiomers are always optically active. What does this negative and positive guys that you see here? When we have dextrorotatory, it means that we have a clockwise rotation of the plane polarized light, and we put positive, so you're gonna put positive. And when we have levorotatory, we have a counterclockwise rotation of the plane of plane polarized light, and we put negative. So you can see these are because of we check them. These are because we check them by the polarimeter instrument, and when they are having clockwise rotation to the polarized light, we have the positive. When they have a counterclockwise rotation, we put negative there. Make sure guys, these are totally different from S and R configuration. S and R configuration is just by numbering based on the priority around the chiral center. But plus and minus, for plus and minus identification, we need to have a polarimeter. Also, they give us in the exam. And this plus and minus also is whenever we have enantiomers. As I said, enantiomers always have R and S opposite R and S configuration. For example, if the left one is R, the right side is S. This chiral center I'm talking about. The left one has R configuration, the right one has S configuration. So these also are mirror image of each other. And when you remove it and you screenshot of the left one and you put it on top of the right one, they are not superimposable. So there are enantiomers. As I said, if you just look at the opposite R and S configuration, you can also figure out if these pairs are enantiomers or not. Let's do this one, guys. I already talked about the right one. We found the R and S configuration for it. Let's do the left one. In here, the right one, in here, the top carbon is gonna be when we put the priority is gonna be R, but because the hydrogen is in the front, we should reverse the configuration. Also for bottom one, the same. Again, these two compounds are enantiomers of each other because first there are mirror image of each other. When you put one to the other one on top of the other one, you see that they are not superimposable, and also they have opposite R and S configuration. See, the left one has a S, the left top has a S, the right top has a R. The bottom left has an R configuration, the bottom right has an S. So they have an opposite configuration from left to right. So that's why they are enantiomers. Diastreomers are another stereoisomer. If you remember, I talked about enantiomers, which are stereoisomers in chiral carbons. Now we're going to talk about the diastereomers, which are also stereoisomers. Diastereomers arise when at least two molecules share at least one chiral center with identical R and S configuration. Let's see how. Look at these two compounds, guys. You can see that at least we have two molecules here, right? Two molecules. The top one is erythrose, the bottom one is triose, which are carbohydrates. We will talk about the L later. You don't need to worry about the L here. So these molecules should at least have one center with the same identical configuration. Look at the top one. Top one is S and S configuration. The bottom one in the left one is R, so it's not the same as the top one. But the bottom right is S, which is the same as the top one. So these two are diastereomers of each other. So diastereomers should at least have one identical same configuration, which these two have, which these are diastereomer of each other, and these are, we call them pair of diastereomers. Important to note that sometimes we might think that we have enantiomers, but we basically have the same molecules. Look at these two compounds. If you start to numbering from the left side, you have R and S, 2,3-dibromobutane. But if you start numbering from right to left, you're gonna have opposite configuration, right? S and R, 2,3-dibromobutane. But it's totally the same, guys. So you can start numbering from the left side or right side. So it both gonna be the same. You know what I mean, guys? So these two basically just depends on from which side you start numbering. You can come up with R and S, 2,3-dibromobutane, or SR, 2,3-dibromobutane. These compounds are called meso compounds. Meso compounds are optically inactive. Pay attention, guys. If we talked about that, enantiomers are optically active, but meso compounds are optically inactive. Also, diastereomers are optically inactive. Non-superimposable mirror images are called enantiomers. Enantiomers always come in pairs. They are optically active. Diastereomers are non-superimposable again and non-mirror image of each other, and always they also come in pairs and they are optically inactive. We also have non-superimposable mirror images are mesocompounds. Mesocompounds have plane of symmetry and also optically inactive. Let's find out how we can find out how many stereoisomers we have. If you remember, we talked about isomers have the same molecular formula. Now let's see how we can find how many stereoisomers we have. This is the formula for it. 2 to the power of n. N is the number of chiral carbons in the compound. Let's see if we can find how many stereoisomers we have for each of these. You can see that I have only one here stereo center, as I have maximum of 2 isomers here. In the second one, I have only one stereo center or chiral carbon. I have maximum of 2 stereoisomers. In this one, I have 2 chiral center. So I put the 2 on top here. I have maximum 4 stereo centers. How you find the stereoisomers in this compound? First, one OH in the left side, one NH2 in the right side. Then you flip these two, one NH2 in the top, one OH in the bottom. This would be another one. Then you're gonna have the OH and NH2 in one side. That would be another stereoisomer. Then you're gonna have OH2 and NH2 in the another side together. So it's gonna be max total of 4 stereoisomers. What about this one, guys? This is cholesterol molecule that we have in our body, and that's control our fat in the body. So we have here 1, 2, 3, 4, 5, 6, 7, 8 stereo centers or chiral centers here. So we have here 2 to the power of 8 stereo centers or 256 stereoisomers for this one. Don't worry, guys, I'm not going to ask you to draw the stereoisomers of this compound in the exam. That's all, guys, for this